So I want to ask a very practical question. How big can we go with nanoscale imaging? Here's the team. Most of the stuff I'll show is from people on the bottom, but in particular Ming Du for a lot of it, who's now at KLA doing mask inspection algorithms for the semiconductor industry. But yeah, that's kind of main personnel showing what I'm doing. And I actually want to kind of step back to some of the discussion we had in connection with connectomics and imaging and ask, if we try and do atomic resolution imaging of molecules, what probe do we use? And I won't go through this in great detail, but I'll just say very briefly that if you use electrons to look at thin samples, that you break about 6 bonds per elastic scattered electron in an organic molecule. If you do it with X-rays, you break something like 500 bonds. So if you're trying to do single molecular resolution imaging, electrons have great intrinsic advantages, and of course that's been realized in cryo-EM. You can't do a single molecule isolated by itself, but you can do a population of identical and combine the information. That's been the secret for cryo-EM, for single particle cryo-EM. There has been this proposal for some time for doing this with X-ray free electron lasers, where you get scattering information before the molecule has fallen apart, and again combined on many identical copies. That's something that still lies in the future, at least at molecular resolution. So electrons are very powerful. We saw, from John's talk how being able to see all the atoms in a very small amorphous particle is really powerful, but they can't do certain things. When you get to samples upwards of a few hundred nanometers thick, you are totally dominated by multiple scattering, by multiple inelastic scattering, by electrons scattered outside of the aperture, and so you just run into a brick wall. They can do high-angle dark field at low resolution as blurred out by multiple scattering, up to about a micron or 2 or 3. There are some examples of that. But yeah, really electrons sort of run against a limit of this intrinsic scattering length that prohibits them from looking at really macro-sized objects. If you look at the same kind of calculation for X-rays, sorting out X-rays into categories of interaction versus sample thickness, you see that X-rays have the potential for going to very, very thick objects. And so we want to ask the question, can we realize that potential? And so this is doing kind of this transport type calculation for looking at the question of biological samples in different ice thicknesses. But let's start small. Let's start with single cells. We can do nice ptychography with single cells. What's shown here is a combination of the focused beam to stimulate X-ray fluorescence. That's at the probe resolution. In this case, it was about 80 nanometer resolution in a cryogenic X-ray microscope. And you see at the left intrinsic fluorescence from elements present naturally in cells at their natural concentration. And so that leads into sort of a whole other topic that I won't really talk too much about. And then you can combine it with ptychography, because this was done in the same scan at the same time, which is the image in the middle where you use the scattered light to get higher resolution. So that's something we do in single cells. And here's just a quick look at what fluorescence gives. This is looking at the process of cell division in fibroblasts, where you really see the chromosomes being arranged by the X-ray fluorescence signal. Now this is not the same cell being followed in time because of radiation damage limitations. It's different cells captured at different times in the cycle. But you can still see very nicely in anaphase the chromosomes dividing there from the fluorescent signals, in this case from zinc, potassium, and sodium. So it's nice to be able to do that, and that's part of a center we have with Tom O'Halloran at Michigan State. And just that if you are doing this ptychography, you want to be able to do it on larger and larger data sample sizes, and so scaling it up onto parallelized clusters is something that we've spent some time on in the past, in particular Yosef Nashed, and you can get pretty good scaling with these reconstructions. And you can also do this in 3D. This was a data set acquired by Zhongjing Deng, and the first 3D alignment was done by John's group here. And then we also realigned it later on with an automatic differentiation approach, which allowed for the alignment parameter tuning. And so being able to do this on a single cell in 3D is very nice, combining ptychography and fluorescence. But what really got me thinking about large-scale samples was I was involved in the early stages of this project for looking at integrated circuits with X-rays. What we have here are some images taken with ptychography by Junjing Deng, then a PhD student with me at Northwestern, where we were able to look at the circuit layers through a whole wafer. So this is looking at the last micron or so of circuit features, but peering through a few hundred microns of silicon. X-rays can peer through thick stuff. And so if we can see these kind of fine features looking through a few hundred microns of silicon, that's completely inaccessible to electrons. That got us worrying about, how big can we go with these kind of nanoscale imaging efforts. Now in the top image, it's before the chip was polished on one side, so you see some scratches with kind of propagation fringes appearing from the scratches. In the bottom is after polishing, where it was a little thinner, and you don't see the propagation fringes from those scratches. But it really shows that you can get good contrast even though you're penetrating a very thick amount of material. And on a different length scale, we've done some work on whole brain imaging, mouse brain imaging, where we do a mosaic version of tomography. Now this is at low resolution. This is at sort of 800 nanometer resolution. It's the scheme of tomography where you just have pure projection of the X-rays through. You use a scintillator to convert to visible light and microscope objective to get the X-ray intensity transferred to visible. That's what limits it to about 800 nanometer resolution. But still, we could do this mosaic tomography approach and do a whole mouse brain at 9 teravoxel data set in the end, reconstructed using Argonne supercomputers. That was work of Ming Du and Raphael Vescovi, to be able to do that kind of reconstruction and then analyze. The sample was prepared by Sean Mikula in Winifred Denk's group. The project lead for this was Bobby Kasuri, then at Chicago, and Eva Dyer did work as a postdoc with Conrad Kording on looking at kind of mean cell distances and distances from blood vessels from this data. Again, we had the discussion on connectomics a little bit. I think the most beautiful images right now on brain tissue done by X-rays are coming out of ESRF, ID16A, where Alexandra Pacurinu, I'm not sure I'm pronouncing her name, I haven't seen her for a bit with COVID, but she's been doing really nice work on looking at neuronal tissue and doing reconstructions on that. I just want to comment briefly that for doing these kind of samples where you have to worry about contrast, that there is some work, embryonic work, let's say, on staining. Lisa Miller has been inspired by what's been done with green fluorescent protein, where you make a cell genetically encode a jellyfish protein that fluoresces, and then you can make cells sort of self-labeled. She's been interested in trying to do that with lanthanides, and so she's done just a little work here with E. coli bacteria, which are genetically programmed to build in europium in their membrane region, and getting a little bit of progress on that. So there's some interest in trying to do this kind of genetic labeling. If you could make a cell, in a sense, or a brain label its own synapses, the neurons label their own synapses, that would be tremendously helpful. That's a long way off, but it's a kind of interesting possibility. But let me get really to the main talk, which is how big can we go with nanoimaging and what are the challenges in doing that? And that gets us back into the basic question of how many photons really do we need to see things? And so I'm going to start with object contrast and influence required for imaging. So the X-ray refractive index is shown here. We have this part that's real, which is the phase shifting part, and the part that's imaginary, which is absorptive. And so F1 is the phase shifting part, F2 is the absorptive part. And what you see for low Z materials is that, it's much more phase shifting than absorption, and that suggests going to higher and higher photon energies to try and make use of the phase contrast. The absorption contrast becomes weaker. But also at the same time, there's a lambda squared there in the refractive index, so the contrast still decreases overall at higher photon energy. So what's the right balance in energy? That's one of the questions we want to get at. And the way we deal with these questions is an approach put forward a long time ago in electron microscopy by Bob Glaser and used by many others, which is to say that in the end we only record intensities in some way or another, whether they're intensities in absorption contrast, intensities from interference and phase contrast, or intensities in diffraction, we're recording intensities. So if we can do a calculation based on the signal we measure, which is the numerator there, the difference between whether there's a feature present or not, times the number of photons, and the fluctuations, which are assumed here to be uncorrelated, and assumed here to be Gaussian fluctuations, which are a pretty close approximation to Poisson, in the denominator, you end up with a very simple expression for the signal to noise ratio you get based on the intrinsic contrast of the material. And you can then use that to say that this is how many photons I need to see. So that's the kind of model we use. And if you write it out for the X-ray refractive index, you can come up with this expression for how many photons do you need. And it turns out that for the cell images I showed you and for the chip images I showed you, this gives you about the right photon exposure for the resolution we achieved in those images to about 20%. So it's actually a pretty good estimate in terms of practical experiments that we do. We think it's a good representative calculation. And it incorporates both absorption and phase contrast. Now this expression here is doing a low order expansion on Zernike phase contrast, but you get quite the same expression for differential phase contrast and for diffraction. And so I think it really is kind of representative of covering all modes of imaging. And what you see is that as the feature gets thinner, you need more photons. That's not surprising. It does less contrast variation. And then as the background material, that's the mu b is the absorption coefficient of the background, and TB is the thickness of the background. That also drives up the dose as you go to a thicker and thicker matrix in which the feature is incorporated. And so the other thing that's a variable here is the signal to noise ratio that you want. People usually assume the Rose criterion. Now in single particle EM, the individual images have signal to noise ratios not of 5 to 1, but more like 1.2 to 1. But still, that's a relatively small factor in all of this. It's really intrinsic to the X-ray interactions. And this all assumes 100% efficiency in doing everything. So with that expression, we can kind of go and calculate fluences and radiation doses. Once we have a fluence, either in photons per pixel, which goes like 1 over the pixel the feature thickness squared, or if we assume isotropic objects in 3D and call that a voxel, we end up with a 1 over feature size to the 4th power scaling for the exposure required. We can then go on and calculate a radiation dose. It's just a number of photons incident times the fraction that are absorbed gives you the dose, the energy deposited per mass. Okay, so if we do that, we can think about it for, this is a 2D calculation, but it's well known from this early work in electron microscopy that the dose in 3D is actually about the same as the dose in 2D. And the reason for that is that in a tomographic reconstruction, you're sort of assembling all the rays pointing back to the voxel where they pass through. And so when you do that, you combine the information from all the viewing angles. And so it works out that the dose that you need for seeing the feature in a 2D image can be divided among all the viewing angles. And that is a very important thing. And it's really tested every day that people are doing single particle EM reconstructions and every day that people are doing CAT scans in the medical imaging community. So it was originally a very controversial idea, but it's absolutely put into practice all the time now. And so what this all tells you is that if you want to improve the resolution, you have to increase the number of photons you use. And here you can see this experimentally. This is work by Junjing Deng doing ptychography, where he changed the dose and sees more and more information appear at higher spatial frequencies, and also in some simulations from Ming Du, where you can kind of calculate this critical fluence that you need to really see features with acceptable signal to noise. And it really turns out that this critical dose here is necessary for getting a good contrast image. Okay, so we see that with a variety of imaging methods. This includes ptychography, it includes near-field ptychography and holography, all in this simulation. And then when you kind of put that together and look at biological samples, you get an answer something like this, that you have this fourth power dependence of dose on resolution. And then I've put on top of here the radiation doses that produce different kind of radiological effects in materials, all the way from killing people at 5 gray, that's the dose that kills half the people exposed without medical treatment, to what it takes to sort of immediately incapacitate the brain of a rat or a pig, to what it takes to kill the very robust bacteria that live inside the cooling pipes at reactors, inactivate muscles from experiments that were done with soft X-rays, all the way up. And you get to something here called the Henderson limit, which is in crystallography. That's the dose that crystallographers go up to. That's the dose where you start to have diffraction spots fade away. So that's where you're breaking bond-to-bond correlation in protein crystals. And then you get up even farther where you start to have bubbling from such a high release of free radicals and hydrogen ions in ice or in water that you start to have this very rapid evolution of hydrogen gas, which causes bubbling in your sample. So if you think of the Henderson limit being a bond-to-bond correlation, that's one thing. When you start to see changes in X-ray near absorption spectra, that's really telling you when you're having kind of significant molecular changes in your sample, and that's around 10 to the 9th gray. So you can go sort of up to doses like that in biological samples that are frozen hydrated and still get a pretty good measure of the sample. Now Malcolm Howells did a calculation where he took data on fading of diffraction spots as a function of diffraction angle and sort of made this combination of the theoretical model that I've shown you with the fading of diffraction spots. And what that shows you is there's sort of this happy zone here where you do not have too much of a dose to cause bond-to-bond correlations to break down and have enough photons to do the imaging. And that sort of points to around 10 nanometers. But I actually think we can probably push a little bit beyond that because we just want mass to stay in place when we're doing microscopy. We don't care if the bonds are broken, just as long as the nuclei are still there and enough of electron cloud around them. So I think we can maybe do a little better than 10 nanometers. That this paper predicted. Now I'll make a couple kind of an assertion here that to first order, all good imaging methods require the same fluids. Whether you're doing ptychography or holography, that they all sort of require the same fluence for the same resolution and contrast of the object. You know, do you get any advantage from signal mixing like you have in holography or in Zernike phase contrast? And I think the answer is no. Richard Henderson in electron microscopy came to the same conclusion a long time before, and I have sort of a little discussion of that in my book on X-ray microscopy. I think the differences from having this signal mixing are very small. So to first order, all imaging methods are the same for the same contrast mechanism. So if we then kind of use that and calculate what is the fluence required for samples of different background thicknesses, same feature size, but different background thicknesses as a function of photon energy on the x-axis and sample thickness on the y-axis, we get curves like this. Now this is sort of a complicated plot, and so I'll tell you what's going on here. The value in white is higher fluence requirement, and the value in black is lower fluence requirement. And then these contour lines here are powers of 10. So this is 10 to the 5th photons per pixel or per voxel in 3D required to do the imaging. And so we see that as you go up in thickness, you need to go up in energy. And it turns out that you can kind of approximate that by saying that the sample should be 1 absorption length thick, because otherwise you'll lose transmission of all the photons that are scattered from fine features in the object. And so, you know, if you go up to samples even of, in this case for copper and silicon, if you go up to samples that are, you know, a millimeter thick, you should be able to do the imaging if you just run up the energy to around 10 kilovolts or thereabouts. And in fact, if you kind of pull the optimum values off of this curve, you get here in blue the optimum photon energy for imaging, in this case for copper and silicon, and the number of required photons as a function of sample thickness. So this is picking the best places on those complex contour plots that were shown here, picking the best out of that. And again, you see that the optimum energy lies very close to making the sample 1 absorption length thick. In other words, tuning the photon energy to make the sample 1 absorption length thick. And if you do the same thing for a biosample, this is what the plots look like. You need more photons, and you have to then also again make the energy tuned to have the sample be about 1 absorption length thick. And here's sort of picking those optimum values off of that plot, again showing you what is the best photon energy as a function of overall sample thickness and the required number of photons. And if you look at the dose rather than the photons per pixel, the radiation dose, you see that the same kind of contour plots here are presented. And you see that fortunately in this case for 20 nanometers is what we picked as the resolution target here, that you keep well below this kind of dose limit of 10 to the 9th gray at which things really truly fall apart, really throughout a wide range of thicknesses. You just have to tune the energy to be appropriate for it. So that's all encouraging in the case of a frozen hydrated sample. Now what happens with a living sample? With a living sample, you have all the creation of free radicals in water and the direct making of bonds in the organic material, and that causes rather drastic effects at much lower doses. So these are some living fibroblasts done quite some time ago in a soft X-ray microscope with absorption contrast, but you can calculate it based on the dose. So at low resolution, because of this 4th power scaling, you can image the live cells that have a culture medium flowing over them and do it quite happily at, this is what, 6 times 10 to the 2 gray, 600 gray. The cells will sort of be reasonably happy for a moderate amount of time. And we actually did, there are these dyes that are red for dead and green for alive that are based on things like ester metabolism. And so we checked against that. But when you up the dose and try and do a higher resolution on live cells imaged in culture, you can see them fall apart dramatically and immediately, even at 10 to the 5th gray. So much lower than the dose that you can reach with a frozen hydrated sample. So that's a real challenge for looking at anything that's living and functioning. Okay, now I want to shift. We've talked about how many photons do we need and can we tolerate those number of photons? And the answer is yeah, we need a lot of photons, but we can tolerate them with a frozen hydrated sample or with a dried sample. And so how many photons can we get? And that gets into the question of coherent flux from diffraction limited storage rings. So back in the 90s, accelerator physicists at Hamburg kind of did some modeling of what would happen for trying to reduce the size angle product, the emittance of electron beams in storage rings. And what they found is that a key parameter is how many dipoles do you have? How many bending magnets do you have that keep the beam going around in an approximately circular orbit? And typical machines have, something like 50 or so bending magnets around. And they said, well, if you could up that to like 3,000, make a lot larger number of weaker magnets, you could really drive the emittance way down. Everyone politely laughed and went on their merry way, because how do you keep a stable orbit while you're controlling 3,000 power supplies? Except then, over time, these multi-bend achromat lattices were taken a little bit more seriously, in particular at Max Lab in Sweden, where they introduced tricks like building multiple magnets onto the same power supply and into the same magnetic block as a way to reduce the number of knobs you have to tune. Now that's not the approach that's being used at many of the other sources, but like so many things, once someone actually tries something, people find a lot of ways to do it. They were the audacious ones to first try this multi-band achromat approach. And what that's meant for the X-ray, the coherent flux available for X-rays, is that we've had this huge gain. It's actually faster than Moore's law for a number of transistors on integrated circuits. And that's pretty remarkable, because we all know how computer power has gone up, and the available coherent flux has gone way up in that same time. So then what I did is I got the best undulator at each photon energy from the advanced light source after their upgrade, which happens in a couple years, and the advanced photon source after its upgrade, which goes dark next year and comes up about a year after. Of course, other facilities are already online and operating, but I took these ones in the US and asked what is the maximum coherent flux you can get at each energy, and sort of made this combined curve. Now you'll see this downward trend at higher energies. That's because they reach a certain brightness value, but the coherent flux is the brightness times the wavelength squared. And so that's what drives these curves down at higher and higher energy. Okay, well, we know how many photons we need as a function of sample thickness, which means as a function of energy that we choose to be optimum for that sample thickness. And so then we can calculate what is the per pixel exposure time. Now this doesn't necessarily mean that we have to do every individual pixel in this time, because in ptychography you're reconstructing many pixels in one illumination spot. And so you're parallelizing a little bit. In a full field microscope, you're measuring all the pixels in one time. And so you're parallelizing even more. Although in full field microscopes, you have to worry about the loss of the lens between the sample and the detector. And so that gets into dose problems. So you do have parallelization here. But if you look at this and do the same thing of plotting the optimum energy at each the sample thickness, which is now a little bit different because we're accounting for the available flux, which goes down as available coherent flux, which goes down at higher energies, you come up with these kind of pixel times. And you know what this says is that for a sample that becomes a millimeter thick of silicon, you've got to have really fast pixel times. So that means you need to have fast detectors and fast scanning if you're doing it by ptychography. And if you do it for a biosample, you need even a little less speed, but still quite fast speeds. And so it looks like a very challenging problem, and it is. But let's ask ourselves about how do we increase pixel time speeds in ptychography as an example. And so we did kind of a algebraic analysis of this a couple years ago. And what we conclude, there are different approaches to doing ptychography. Do you use a small spot and scan really fast? Do you use a big illumination spot where you don't have to scan with as many steps and the step sizes can be larger? What's the optimum? And it turns out you can show that if you have the same flux rate and decide as a variable how big to make that beam, you can choose as you wish and get the same data flow rate coming out. So it really becomes a choice, and the advantage of a small beam for ptychography is that you need fewer pixels in the detector, but you need a higher frame rate. And the advantage of a large beam in ptychography is you need a much slower frame rate for the detector, but you need a lot more pixels to the detector. So again, the net information flow is the same in each case. The other thing with a small beam is you have less coherence width across the sample. You can tolerate broader monochromaticity in doing a single mode reconstruction. Okay, what else gets into being a challenge for doing large samples with nanoscale imaging? And one of them is a depth of focus limit. So the depth of focus limit, it's basically lambda over the numerical aperture squared for depth of focus. And you can write this down in a different way as a function of transverse resolution here and photon energy, which is shown on which color of line there, and you get the depth of focus out. And what you see is that, well, if you're going to do nanoscale imaging on a big sample, you're going to go beyond the depth of focus. You have to deal with this problem. You can't do simple pure projection tomography when you go to high resolution, no matter what practical photon energy you choose. You're going to have to worry about depth of focus problems. Fortunately, they're addressable. We heard a little bit about that from Laura Waller's talk this morning. Basically, you can do this multi-slice type propagation, beam propagation method. We heard about that a couple times. You can incorporate that into the forward model where you have the refractive effect of a thin slab applied to the wave, then do free space propagation to the next plane, and so on. So you can account for this in the forward model and thus build it into the reconstruction. This was done for doing discrete planes in ptychography, first by Andrew Maiden, where they did reconstructions of several discrete planes. But we wanted to do it for continuous objects, and so our example of that, the first one was Mark Gillis, who was here. Yeah, Mark's here, yeah. So he did this while intern with Stefan Wild at Argonne, where you build the multi-slice model into your forward model, and just do an optimization approach and do a reconstruction. In this case, I think it was a 256 squared cube, right? Or yeah, and parallelize on Argonne supercomputers. So you can do it, and you can see that doing the multi-slice version, which are the two Moore panels at the left, is much better than not incorporating propagation effects and depth of focus effects into the reconstruction. You get a much better answer for the reconstruction. And then Ming Du re-implemented that using automatic differentiation approaches, which allow you to more easily incorporate other regularizers in. And so, again, got nice reconstructions for small size objects in computer simulations. So, and experimentally, it's been done with electrons and so on. So we think that's a solvable problem if you have a coherent wave. You have to have a coherent wave to be able to do the forward and backward propagation that applies to multi-slice modeling. But if you have that, you can do it. So then what about how big an object can we do wave field propagation with? That was something Sajid Ali looked into. He really liked playing around with supercomputers, and so he wanted to ask, how do I most efficiently do large-scale wave propagation calculations when I have parallelized computers? And he compared a couple approaches. Tim Saldut's group has done beautiful work with the finite difference approach, and it turns out that that's nicely incorporated in some of these supercomputing software packages. And so there was a nicely implemented parallelized version of finite difference. And then we did a Fresnel multi-slice version where you kind of break the problem into tiles. You build sort of a guard region around each tile for diffraction from one plane into the next plane to be ignored or to be ignorable. So you can do this kind of tiling-based approach to multi-slice. And you get good scaling on supercomputers. You can actually solve these kind of problems on big enough arrays to make it possible to consider doing these kind of reconstructions. One more thing we need to worry about, which is how many tilts do we have to make on a sample if we do this multi-slice reconstruction. And so, of course, there's the famous Crowther criterion, which tells us that the number of rotation angles we need for complete filling in all of Fourier space in 3D requires us to take a number of tilt angles, which are basically pi over 2 times the number of pixels across in a 2D image. It's expressed slightly differently in Crowther's original paper, but that's basically what it works out to. And that comes from saying that if you have pure projection images, you have no pixel depth in the Fourier transform along the beam direction. You just get a plane. But you have pixels along the transverse direction. And if you sort of ask about how do I fill in 3D Fourier space with all these projections without leaving gaps at the corners, that's how you come up with the Crowther criterion. Now, we all know that when you include other tricks in tomography, like regularizers and so on, that you can do fewer tilts than this by far. We've heard talks about that, for example, from George. But still, it gives us a rough idea, a scale for how many tilts we need. Well, if you think about doing the multi-slice problem, where you're actually reconstructing planes using Fresnel propagation between those planes to distinguish them, then it turns out you're filling in Fourier space a little bit differently. You're reconstructing these separate planes along each axial direction, and so you get not a single pixel deep along that axial direction in the Fourier plane, but multiple pixels deep. And then if you ask yourself how many rotation angles do I need to fill around the circle in Fourier space, it turns out that you just divide by the number of axial planes that you've reconstructed. So if your sample is 10 depths of focus thick, you need a 10th fewer rotation angles to fully fill in Fourier space. And again, you can play the same tricks of doing less than the Crowther criterion number of tilts, but it still gives you a scale for that. And it turns out even kind of nice that you get some cancellation of factors so that the number of tilts in this multi-slice approximation works out to just scale with the transverse resolution over the wavelength, independent of the overall sample size. Okay, so if we put all of this together, how big can we go small? Can we really contemplate in the future doing macro sample imaging at nanoscale resolution? So we put together the times for the imaging and the available coherent flux and all that. The optimum photon energy is a function of sample thickness, and we come up with rather wild numbers like this. So this includes pretending that you did everything with 100% efficiency. There was no wait. Yeah, there was no wait time for stages to move around. Nothing like that. If we do everything in a perfect world, how fast could we go? Well, this suggests that we could do circuit features in a chip, in something like a minute for a millimeter 3D sample. Now, chips are, of course, planar, but still, it portends a future that's rather encouraging for doing macro size sample imaging. And if you look at the biosample, where the contrast is lower, this is just using intrinsic contrast of protein against ice. So it's not assuming any contrast boost from staining. If you consider, like a whole mouse brain, which is on the order of a centimeter size, this suggests that you should be able to do a whole mouse brain at 20 nanometer resolution in a week. So again, there's a lot of optimistic assumptions in this, but it at least gives one hope to think about how to do macro size objects in the future. Because again, the beauty of X-rays is they penetrate thick things. They have short wavelength, yeah, and we use that for high resolution imaging. But what really distinguishes X-rays is that they can do thick stuff. And how can we exploit that and really do thick sample imaging? Another thing with X-rays is there's no cloudy days with X-rays. Why do I say that? Clouds, of course, involve plural elastic scattering, multiple scattering of light, so we can't see through the path through a cloud and see what's behind it. With X-rays, the coefficients for scattering are less than the coefficients for absorption or the refractive effect, the overall kind of bulk refractive index effect. And these calculations from Ming-Du that I showed the very complex contour plots of incorporated multiple scattering as a background signal. And so it really gives us hope that we can imagine doing nanoscale imaging on macro size objects. So that's sort of the end of the story, that I think it should be possible. There are a lot of challenges. You have to make faster detectors. You have to learn how to prepare samples that are that thick. We had some work on trying to do high pressure freezing of very thick samples, which was not as successful as we hoped. Even at higher pressure, you still have some time for the temperature gradients to build up, and that still does some disruption in tissue. So we don't have an answer to that yet, but still it's something worth thinking about for the future. And with that, I'll say thanks again for people like Ming-Du and Sajid, Saugat with automatic differentiation, Pan on X-ray fluorescence more, and Xiaoling Jin for those looking at dynamics in cell division. And then thank you all for your attention.